Hello everyone, Bill Stubbs here, back with the third video in my series, Dissecting the Standard Model of Particle Physics, I call Who Invited the Pions? In this video, I continue discussing the contents of my book, Three Quarks Missed the Mark, by taking another look at the electron-proton deep inelastic scattering data that ultimately led to the formation of the quark-gluon model of the proton, and showing that data from later experiments reveal that some of the assumptions made en route to establishing the quark model were not valid and point to proton constituents commonly found in nature. Let's get to it. In the last video, we saw that when the SLAC proton F2 curve did not behave in a way that supported Gell-Mann's three-quark model of the proton, assumptions about how the data would behave in the untested region between x equals 0 and x equals 0.08 were made that allowed the three quarks to be retained in the proton, but with a population of quark-antiquark pairs. In 1993, the Hadron Electron Ring Accelerator, HERA, began operating. The initial HERA runs were from x equals 0.133 to x equals 0.000178, which covered most of the x equals 0 to x equals 0.08 range left out of the SLAC runs. In HERA, both the electron and the target move, allowing the collisions to occur at much higher energies and momentum transfers than in the fixed target linear accelerators. The first experiments in HERA used 26.7 GeV electrons and 820 GeV protons that produced momentum transfers from 4.5 GeV squared up to 1600 GeV squared, compared to the 1 to 8 GeV squared momentum transfers achieved in the first SLAC experiments. The center of mass energy for colliders is approximately the square root of 4 times the product of the electron and proton energies. With an electron energy of 26.7 GeV and a proton energy of 820 GeV, the center of mass energy for the HERA runs is 296 GeV, about 40 times the SLAC center of mass energy with a 30 GeV electron. It would take an electron energy of nearly 47,000 GeV to generate an equivalent center of mass energy in SLAC. The HERA electron-proton collision energy of 296 GeV results in an electron wavelength of about 0.0042 Fermi, which is roughly 400 times smaller than the diameter of the proton. The HERA results reveal that F2 did not appear to be constant between x equals 0 and x equals 0.08, but actually rose up to nearly 5 times its average value at x equals 0.08, as seen in the graph showing. This was actually encouraging because it supported the idea that, in addition to the quarks, the proton also contained gluons, which were added to the model from work by Julius Kuti and Victor Weisskopf to balance the momentum distribution between the three types of quarks. Without gluons, the strange quarks appeared to carry about 76% of the proton's momentum, compared to 18% for the up quarks and 6% for the down quarks, possible but a seemingly skewed distribution. By adding gluons, Kuti and Weisskopf showed that gluons carried 34% of the momentum, the up quarks 29%, the down quarks 19%, and the strange quarks 17%, a more likely distribution of the momentum. So, it seems that while the Berkane-Pascos assumption wasn't totally correct, it was in the right direction and ultimately led to what seemed to be a valid proton model. But there's more to this story than meets the eye. As mentioned earlier, the range of momentum transfers in HERA, 4.5 to 1600 GeV squared, start at the top of the SLAC's 1 to 8 GeV squared range. Just how compatible are the two sets of data? It turns out most of the early runs in SLAC were done at or below momentum transfers of 3 GeV squared, while none of the HERA data fell in that range. This is important to note because it means that the wavelengths of the electrons that produced the HERA results were much shorter than those that produced the SLAC results. So, consequently, the HERA electrons saw something different from the SLAC electrons, and the two pictures probably were not compatible. There was, however, some electron-proton deep inelastic scattering data generated in the x equals 0 to x equals 0.1 range, with Q-squared values comparable to the SLAC values. We will come back to the HERA data in the next video, but now we turn to data generated by the Thomas Jefferson National Accelerator Facility, also known as the Jefferson Laboratory, or JLAB, in 1999 and 2000. The JLAB experiments were fixed target experiments like SLAC with electron beam energies up to 5.65 GeV and momentum transfers from 0.034 to 2.275 GeV squared, comparable to the Q-squared values for SLAC experiments with x less than 0.17, most of which were less than 2 GeV squared. This data is more congruent with the SLAC runs from the 1960s that the quark model of the proton was founded on than the HERA experiments from the early 1990s. The JLAB X values ranged from 0.009 to 0.45, the range not covered by the SLAC experiments. When the JLAB data is combined with the SLAC data, it produces a curve like the one shown. For the range from x equals 0 to x equals 0.08, as x approaches 0, the JLAB F2 values also approach 0, just as Berkane and Pascos initially expected them to do. However, they peak at about x equals 1/8 or 1/9 instead of 1/3, indicating there are 8 or 9 particles inside the proton, not just 3. If the particles are spin 1/2 particles, then a candidate for them is the muon. With a mass of 206.768 electron masses each, 9 muons, 5 positive and 4 negative, have a total free mass of 1,860.912 electron masses, 24.759 electron masses greater than the proton's 1,836.153 electron masses. This allows for a binding energy of about 13 MeV, less than half that of the alpha particle, which seems a little weak. But for their spin zeros, pions could also be a candidate for the proton components. 8 pions, for example 4 positive, 3 negative, and 1 neutral, provides the positive charge, and with the charged pions having a mass of 273.133 electron masses, and the neutral pion 264.143 electron masses, the 8 pions have a total free mass of 2,176.074 electron masses. This is 339.921 electron masses, or 173.7 MeV, available to bind the particles together within the proton, 13 times the binding energy of a proton made of 9 muons. Furthermore, sometimes when protons collide with antiprotons, 8 tracks appear, 4 positive pions and 4 negative pions, suggesting that the components of the two particles are pions. Clearly, the pions are a more attractive proton component than the muons, but protons contain spin 1/2 particles like the muons, or do they? Virtual photons can be either longitudinal, requiring the target to have cross-section sigma sub L greater than 0 to absorb them, or transverse, requiring the target to have cross-section sigma sub T greater than 0 to absorb them. The electrons emit virtual photons with helicities of plus or minus 1, making them transverse virtual photons. Spin 0 particles absorb longitudinal but not transverse virtual photons, while spin 1/2 particles absorb transverse but not longitudinal virtual photons. Callan and Gross determined that for particles inside the proton, the two equations shown hold. Therefore, for spin 0 particles, since sigma t equals 0, f sub 1 equals 0, and for spin 1/2 particles, since sigma L equals 0, f sub 2 equals 2x f sub 1, or 2x f sub 1 over f sub 2 equals 1. This means that if the measured f1 and f2 structure function data satisfies the ratio 2x f sub 1 over f sub 2 equals 1, then the particles inside the proton are spin 1/2 particles. But if they satisfy 2x f sub 1 over f sub 2 equals 0 when x is not equal to 0, then f1 must equal 0 and the particles inside the proton are spin 0 particles. If the ratio falls between 0 and 1, then the virtual photons are apparently encountering a mix of spin 0 and spin 1/2 particles. The graph shown is a plot of 2x f sub 1 over f sub 2 shown earlier to show that for x greater than 0.25, the ratio hovers about the value 1.0, interpreted to mean the virtual photons were seeing spin 1/2 particles inside the proton. However, for the particles the deep inelastic scattering found inside the proton, x falls between 0.10 and 0.125. Since the photons probably cannot see the particles inside the proton at x greater than 0.25, they are likely responding to the entire proton. The spin 1/2 they see there is the spin of the proton. For x less than 0.25, the ratio appears to be steadily declining. This likely indicates that as the x values get smaller, the virtual photons are encountering spin 0 particles along with seeing the whole protons spin 1/2. This suggests that as x gets smaller and the virtual photons focus in on the particles inside the proton, they are encountering spin 0 particles. The virtual photons not being able to see these particles, combined with them still being able to see the entire proton, slowly causes the overall 2x f sub 1 over f sub 2 ratio to get smaller for x less than 0.25 as x approaches 0, as shown in the graph showing. Now, the particles inside the proton look like spin 0 particles, pions, not the spin 1/2 muons. Since we know how big the proton is in terms of radius, we can get an idea of what the radius of a pion might be. The proton's f sub 2 curve peaks at about f sub 2 equals 0.36 and is a blunt peak. According to parton theory, a blunt f sub 2 peak, much less than 1, indicates that the particles found in the proton interact strongly with each other. At a minimum, this means that they are probably tightly packed within the perimeter of the proton. Assuming the pions are spherical and that all three types are the same size, then the 8 pion spheres, tightly packed, form the proton virtual sphere, whose radius is 0.875 times 10 to the minus 15 meters. The smallest container sphere, 8 identical smaller component spheres, tightly packed, can fit into is one with a radius 2.646 times the radius of the smaller spheres. This makes the radius of the component spheres 0.378 times that of the container sphere. Therefore, the radius of the pions appears to be about 0.378 times 0.875 times 10 to the minus 15 meters, or 0.33 times 10 to the minus 15 meters. The next video will show why even the pions are not the fundamental components of the proton.